Plankton, when's the next karate session?
Forget karate. Our Stokes theorem assignment is due today.
Stokes? Is that the guy from last week? He still wants money?
No, SpongeBob. It's a math theorem.
Someone please explain it. You explain it. You're the tutor now.
Hello everyone, today I will be explaining about Stokes theorem to all of you as well as to SpongeBob. So Stokes theorem relates the line integral around a closed curve as well as the surface integral of the curve over the surface it bounds. So basically this is a visual representation on what I just said, where green is the rotation of field inside the surface and the red is the circulation around the bounds. So the bounds is the blue one that is surrounding the green. So this is basically a display of Stokes theorem. Okay, let's go over the formula for Stokes theorem. We know that we get the line integral of f dot dr, which equals to double integral of nabla times f dot nds. So this thing, nabla times f, is basically just the curl of the curve and nds. So to put it into perspective, this left side of the equation is basically the circulation around the curve. So let's go back to our diagram over here. See, this left side is basically all these red lines. So when we find this, we find the red lines of this. And this right side of the equation, double integral blah 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 blah, is the rotation of field inside the surface. So these little green rotations things inside, right? So that is what we're calculating with this formula, with this side of the equation. So here's a little bit more explaining so that you guys can fully visualize how Stokes theorem works. Okay, so line integral is the circulation, as I said just now. This thing, the bound, and the curl, as I said, this is the curl. The curl is the rotation inside of it. So line integral circulation, how much the field pushes. See how much it pushes so it can expand or whatnot. And rotation inside the curve is how much it spins, or how much it spins within this area. Okay, so let's get into examples. Here I got example 1 over here. So what is given is this diagram. We know that f, negative y, x, 0. So these are the coordinates for f. And we know that c is x squared plus y squared equals 1, which is basically a circle. Hence the visual representation over here. So first of all, let's look at this. Let's recall the Stokes theorem, which is right here, and let's try to do this question. So first of all, first step is to compute the curl. So as I said, Stokes theorem includes curls, which is nabla times f. So here is just I, j, k, and then we find the differential of x, differential of y, differential of z, which in this question we get 2k as the final. Next we do the dot product. Again, we're going over this side of the equation. So now we're finding the dot product. So we do the curl times n, where n in this case is basically 0, 0, and 1. And if you don't know what n is, here it is explained. N is the unit normal vector to S, where S is the surface bounded, right? Okay, so we do the dot product, and after doing the dot product we get the answer of 2. Next we set up the integral. So we set up the integral and fully finish off this side to get the final answer, because in this question, as stated here, we have to find f.dr. So we do the integral, and finally we end up with a solution of 2 pi. So the answer for this question is 2 pi. So line integral of f.dr is basically 2 pi. Okay, let's go to our next example, example 2. Again, we recall Stokes' theorem over here, and given information is this: C is triangle in plane, where triangle in plane Z equals 0. So this is one sentence, by the way. C is triangle in plane Z equals 0 at 0, 0, 0, 1, 0, 0, and 0, 1, 0. Okay, now we know that, and we can see this diagram. Let's compute the curl. Let's compute the curl like we did in the last question. Alright. So you see here, after computing the curl, we get 0. Now, once we get 0, everything which will be times by 0. So that would mean that the dot product is also 0, which would also mean that it is 0. So what this basically means is that there is no net circulation. So there's nothing circulating around this thing. Okay, so usually, like in this case, this circulation is 2 pi, but in this case nothing is circulating around it. So that means it's just there. Alright, so in case all the examples I've given so far still hasn't really, you still can't envision it, here's a real life implementation on when we use Stokes' theorem. So over here we have a drone propeller. Okay, this is how a drone propeller looks like. Right, it's just alright, the thing in drones. Okay, so engineers will calculate the airflow around the outer bound. So it'll calculate the airflow around this area, around this, all this. Now Stokes' theorem converts that data to boundary, which is to put it simply, basically with Stokes' theorem we're now able to figure out the rotation inside this with just calculating the outer bounds. So this would make it easier rather than having to calculate every single little thing within the bounds. Alright, so yeah, that is basically Stokes' theorem. I hope this helped you guys, and yeah, I'll bring you guys back to SpongeBob
Later. Wow, I actually understand Stokes' theorem now.
Me too. Actually, no, but good job.